Start recording. So which of those ions will form the buffer? Which of those ions will form the buffer? HCO3 minus. Whoops, I'm erasing instead of highlighting. That's not helpful. HCO3 minus and CO3 minus, okay? HCO3 minus and CO3 minus, because then you can get this equilibrium set up. Actually, could you write this equilibrium two different ways? Include water in there. Let me know if you'd like a hint. Like a hint? Okay. All right. So in equilibrium number 1, what will our products be? CO3 minus, because we have to have both species, right? And who is our other ion? H3O plus. And who is our other reactant going to be in equilibrium number 2? CO3 minus. Now, if CO3 minus is the reactant, what do we get as our product? HCO3. Whoa. HCO3 minus plus OH minus. And to be honest with you, it doesn't matter which of these two equilibrium that you write. I usually go with the acid one simply because we are given a bunch of Ka values and it makes our lives easier, but it doesn't really matter that much. Okay? So, as long as you have a weak acid and its conjugate weak base, or you have a weak base and its conjugate weak acid, then you have a system that can buffer. Is good? And to be honest with you, there's not a lot on buffers in Chemistry 12. Okay, we're not going to do any calculations with them. What we're going to do is we are going to go back to, is it 5.4b? No, let's see. No, 5.5b. There we go. Okay, so we're going to hop back here and we're going to go to page 81. So if you remember from last day, buffers are mixtures of either WASCABA or WUB-SCA. The weak acid and the salt of its conjugate base, or the weak base and the salt of its conjugate acid, and everybody has to have a large concentration. And we usually try to have the concentrations of the weak acid and the weak base to be approximately equal. Now, this next bit makes me unhappy, but this is what's included in the Chem 12 curriculum. In general, if you want an acidic buffer is one that buffers at pH less than 7. You will use a weak acid and the salt of its conjugate base. So for example, if our weak acid were HCN and we had it at about 0.5 molar, the conjugate base would be Cn minus, which we would put in the form of NaCN. And what concentration should we have it at approximately? 0.5 molar, approximately, okay? So pair the Cn, of course, with a cation that is soluble and does not hydrolyze any alkali ion, but Na is our favorite. Could you write the equation for the equilibrium formed by the above buffer system? And if you're dealing with a buffer system, you don't want any spectator ions. So you can write it either way, okay, with the water or without the water. Does that make sense? In fact, you could even, if you wanted to, write it this way, Cn minus plus H2O in equilibrium with HCN plus OH minus, but I feel like that's just overly complicating things. Do you know what I mean? Like you could write it that way, but why would you? When you have a very tidy reaction using the acid. Now, if you want a basic buffer, what do you think you would use? You would not use, in general, a weak acid and the salt of its conjugate base. You would use a weak base and the salt of its conjugate acid. Okay, so we have NH3 and NH4. Now we have to pair the NH4 with an anion. Chloride is a good choice. Nitrate would be another good choice. Okay, they don't hydrolyze. And if our concentration of ammonia were 0.7 molar, what do you think our concentration of NH4Cl should be? Approximately 0.7 molar. Write the equation for the equilibrium formed by this buffer system. Is good, so you can either write it in the base form or you can write it in the acid form without water, or you can write it in the acid form with the water. Now, I cheaped out and I did not make separate workbooks for you guys in the AP so that for AP we go into the math more and we see how we can actually make a basic buffer from a weak acid and the salt of its conjugate base and vice versa. But for the most part, acidic buffers use a weak acid and the salt of the conjugate base. Basic buffer use a weak base and the salt of its conjugate acid. And really, that's all there is to it. I know it seems like we've spent a lot of time on buffers, but oh yeah, we still have to talk about buffer capacity, although we've already talked about it. What is buffer capacity? What is capacity? How much, right? So a buffer capacity is how much H plus can we add before the buffer gets overwhelmed and cannot shift anymore? Okay, so capacity is how much. How much H plus or OH minus can we add before we run out before we use up all of the weak acid or the weak base? It's known as the capacity of the buffer or the limit of the buffer. And the buffer's capacity is determined by the number of moles of the weak acid and the number of moles of the weak base. The higher the number of moles, the higher the capacity. The lower number of the moles, the lower the capacity. Which brings us to questions like the following. Of the following 1 liter solutions, which has the greatest buffering capacity? This just requires you to know what buffering capacity is and how to recognize it. Chat with your neighbor, see if they agree with you. Oh, your neighbor abandoned you. I'm so sorry. Do you want to vote? Okay, this is A. This is B. This is C. D, you put your pointer finger up and you make a circle with the rest of your fingers. That's D. And then E looks like this. So fingers in and thumb curled. So 5, 4, 3, 2, vote. Yes, it is B, because we have the most number of moles. We won't run out as soon. If you have a lower molarity, you'll have a lower number of moles, and they're all the same volume, so that doesn't affect it. Okay, so the answer is B. Most moles won't run out. So let's say we have a buffer solution that's prepared by using 1 molar acetic acid and 1 molar sodium acetate. That means we have 1 molar of CH3COOH and 1 molar of CH3COO minus. And let's say that we have 1 liter of this solution. How many moles does that mean that we have of the acetic acid? How many moles of the acetic acid? If we have 1 liter of 1 molar, this is easy. 1, we have 1 mole. And how many moles do we have of the acetate? We have 1 mole. Now, let's say we add 1.5 moles of HCl. What's going to happen first is that the H3O plus goes up to 1.5 molar. This is more than the CH3COO minus can react with. Yes, because these guys react 1 to 1. So we're going to have an excess of 0.5 molar of the H3O plus. So we have overwhelmed the buffer. The buffer has gone beyond, we've gone beyond the buffering capacity. Does that make sense? Okay, and let's see. Key points. A buffer cannot be made from a strong acid and the salt of its conjugate base, nor can it be made from a strong base and the salt of its conjugate acid. Buffers have to be made with weak acids and weak bases. Why can we not make a buffer with strong acid? You guys told me this last day. Yeah, you can't establish an equilibrium. Now, there is an alternate way to make a buffer, but I'm not going to teach it to you, okay, because it's AP. If you would like to know about it, you can ask me about it later, or you can go through the answer key. The answer key has it all filled in for you, okay? All right, we are moving on now to titrations. So once again, slow Ms. Spence. My videos are like 20 minutes, 25 minutes, blah, 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 blah. More videos. Oh my God, titration curves are big. Or you can watch Mr. Colger. 6 minutes, 8 minutes, 9 minutes. Ooh, the big long one is 11 minutes. Okay, so feel free, if you're not understanding when I'm done, to use these as resources. Okay, this is on pages 89 and 90. All right. That's all we're doing with this, though. I'm just pointing out that you have those videos should you want to watch them. And now we're going to go on to page 91. And we're going to look at titration curves, which is basically the graphs. And it's going to be the graphs of pH versus volume. Now, do you remember doing your titration? We had a burette filled with a known concentration of NaOH. Do you remember what we call a solution with a known concentration? The known concentration is called the titrant. Okay? The known concentration is also called a standard solution. So, known concentration is the titrant or the standard. And what we're going to do here that's a little bit different than what you did in your titration lab, you just went along and watched until it changed color, yes? This one, we're actually going to stick a pH meter in it. Okay? And there's a stirring bar at the bottom, so you can it'll just keep stirring for you. All right? And we can record the pH at every volume that we want to. And in fact, if you get you can actually get a pH probe, and you can have an automatic titrator, and it will actually record the volume and the pH for you all at once. It's really nice, and then it'll graph it for you on your graphing calculator, but we don't have any of those because we're not fancy like that. But maybe at university you'll get one, okay? So down here we have our HCl of unknown concentration. Do you remember what we call the unknown solution? It's called we're going to analyze it. Therefore, it is called the analyte or the sample. Okay, oh, there's a go figure question. Let's read what that go figure question says. In which direction do you expect the pH to change as NaOH is added to the HCl solution? Do you expect the pH to increase or decrease as we add NaOH? It's becoming more basic, so the pH should increase. Okay, so here we have our burette, we have the titrant, which is also known as the standard. I'm going to get rid of this word titrant because it's just confusing. We'll put sample there instead. Okay. We have a conical flask, also known as an... What do we call those flasks? Erlenmeyer. So nothing much new so far. Do you guys remember what the equivalence point is? See if you can define it without reading the definition. The equivalence point. The point at which the acid / base has been completely neutralized. Now, it gets a little more complicated than that if we have a diprotic acid, but we will not be dealing with that in chemistry 12. Okay, so we're not going to worry about it. So, in other words, it is the point in the titration where the amount of titrant, that is our known, added is enough to completely neutralize the analyte, our unknown. And basically what it ends up being is that the moles of acid equals the moles of base, although it would be better actually to say that the moles of OH minus is equal to the moles of H plus. The solution will contain only the salt and water. All the acid's gone, there's no extra. All the base is gone, there's no extra. All that's left is the salt and water. What is the pH of the solution when we hit the equivalence point, when all that is left is the salt and the water? You've got 4 choices: acidic, basic, neutral. You can't tell from this question. Chat amongst yourselves. So acidic, basic, neutral, or not enough information. Chat. Convince yourselves. Okay, we're going to vote again. This is A. This is B. This is C. For D, you put your pointer finger up and you make a circle with your other fingers. Oh, and there is no E. So do we like A, B, C, or D? Or you can also vote this way. I don't know yet, which is totally fine because you might not know yet. 5, 4, 3, 2, vote. What? A is acidic, B is basic, C is neutral, D is not enough information. That would be helpful if you knew those ones. Okay, I got some I don't knows, I got some C's, I've got some D's, I've got some more I don't knows. Okay, the answer is D. Oh, there's not enough information. What do we have in our beaker when we've neutralized all the acid and the base? We have salt and water. What do we know about salts? They might be able to, their ions might be able to hydrolyze. So we don't have enough information yet because I haven't told you what the salt is. Okay, so maybe hydrolyze. And that means we have not enough information. Define the term indicator to your partner. I have to tell you guys, I don't like my definition. My definition is actually wrong. See if you can figure out what's wrong with my definition. It's in the first line. An indicator is a weak acid or base that is added to the analyte, the unknown, solution. So there's a mistake in that first line. It's a weak acid plus conjugate base combo. Yeah? It's a weak acid plus conjugate base combo, so I need to fix this. Or maybe I don't fix it and I just go through this process every year and get you guys to correct it. And if you choose the indicator correctly, that's hugely important. It should change color when the equivalence point is reached. If you choose the indicator poorly, it will not change color at the equivalence point. Thank you. You can just throw everything in there. Mm-hmm.
But it's the last quiz.
The last quiz?
Yeah.
Oh.
I did it yesterday.
Oh, yes. Yes. Where did I put them all? They are here. Yeah. So if you choose the indicator poorly, it will not change color at the equivalence point. What do we call the point at which the indicator changes color? It's called the transition point. It is also called the end point. If you choose your indicator well, the end point and the equivalence point will be at the same point. If you choose it poorly, they will be at different points. So what is this titration curve? Well, we take the plot of the pH and we graph it. And if we have our base, and if we have in our flask our acid, does it make sense that when we're measuring the pH, that the pH starts low and finishes high as we add the base? So this is the pH of the analyte solution, which is the acid, and this is the volume of the titrant, the NaOH added. And you'll notice, what kind of a shape is that? What does it look like? The letter S. An S-shaped curve is sigmoidal. You don't need to know that. The Greek letter sigma is the Greek letter S. However, when you write a sigma, it does not look like a letter S. It looks like that. Okay, so that's a Greek letter sigma. Anyway, you don't need to know any of that. That's just kind of me geeking out on Greek. Greeking out? I'm Greeking out, yes. All right, so now we're going to look at the most common and easiest type of titration. This is a strong acid with a strong base. And you guys just wrote a quiz yesterday about mixtures of strong acids and strong bases. Okay, so we're going to deal with hydrochloric acid, our strong acid, and NaOH, our strong base. And our titration curve will look like this. And we're going to take a note of all these little points here. We got point 1, point 2, point 3, and point 4. Okay? At point 1, we have added no NaOH, none. So it is just the hydrogen coming from the HCl, okay? So you just have HCl, and if your concentration, let's say, for example, this was, oh, I can't do that yet. Okay, we'll come back to it later. Oh, actually, what is the concentration of the HCl? There is enough information on that graph that you can tell. And we've only gotten to point 1, so my guess is it's probably going to come from point 1. Are you guys telling me you need your calculator to do this? Seriously? Go ahead, use your calculator. It's okay. The pH is 2. I know. Therefore, the constant 10 to the negative 2, right? Yeah. Equals 10 to the negative 2. Yes? And that's just 0.01 molar. Yes? So technically, we wouldn't even need to do this thing. But if we didn't know that it was a strong acid, we might have to, because weak acids do their own thing, right? You'd have to do a rice table and all sorts of stuff. Now, between points 1 and 2, we are adding NaOH, but we still have excess acid. Yes? So between points 1 and point 2, we have excess acid, and that explains why the pH is still low. Now, point 2. It's recorded just before complete neutralization. And then what happens to the pH when we get to that complete neutralization? It increases dramatically all at once, right? How much volume do we add? How much volume is added between this point and that point there? Almost nothing, like a half a drop maybe. So this is why when you are adding those drops, it's like nothing, nothing, nothing. Oh, I think it's okay. Oh my God, it's all pink now. Yes? Because you're sitting here and you're like, nothing, 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 pink. Yes? So if you go past even like one drop, you'll end up probably with a more pink solution than you would want. Yeah? And that's because you go from having excess acid to the equivalence point. Now, what is happening at the equivalence point? There is no excess what? Acid, and there is no excess base. And then afterwards, from point 4 onwards, so that's our equivalence point, we have no excess acid, no excess base. Why is the pH so high from point 4 onwards? Well, what are we doing? We're still adding titrant. And what is the titrant? The titrant is the NaOH. So we're still adding NaOH. So we had excess acid. We neutralized all the acid. And now we have excess base. So at the equivalence point, the acid and the base have completely reacted with each other and they are all gone. What do we have left? We have a salt and water. Now, what I'd like you to do is I would like you to tell me about this salt, which is made up of Na plus and Cl minus. What is the pH of that salt? Does Na plus hydrolyze? No. Does Cl minus hydrolyze? No, because its conjugate acid is strong. So if you have no hydrolysis, what kind of a salt is this? Is it an acidic salt, a basic salt, or a neutral salt? No hydrolysis. Therefore, neutral salt. And therefore, what's the pH? Therefore, the pH is 7. So if you react a strong acid and a strong base, you're going to get a salt that does not hydrolyze. Okay? Strong acid plus strong base will give you a neutral salt. And that's why, if you look at our equivalence point, if we go back up here, what's the pH at the equivalence point? It is 7. Okay. So NaCl is present, which is a neutral salt, and therefore we are at pH 7. Thank you. And we're just getting in there, so some good. Yeah. Okay. As the NaOH continues to drip in after the equivalence point, it starts to become basic because we have NaOH, which dissociates and gives us OH minus. So we have excess OH minus because all of the HCl is gone already. We good with that? All right, moving right along. We already did this question. According to the graph on the left, what is the initial concentration of the HCl solution? And that was pH is equal to 2. So the concentration of H plus was equal to 10 to the negative 2, which is equal to 0.01 molar. Now it's written somewhere nice rather than squashed in. And now you get to try the next go figure question. What volume of NaOH, okay, and NaOH is what we are adding, okay? What volume of NaOH would be needed to reach the equivalence point if the concentration of the added base were 0.2 molar? Now, right now, in this particular picture, it tells us that the concentration right now is 0.1 molar. So what we're saying, you can ignore the little diagrams down below. We'll talk more about those later. But this NaOH right here is 0.100 molar. And what the question wants to know is, what volume would we need if the NaOH were 0.2 molar? What volume to get to the equivalence point? That's supposed to be a question mark. I'm going to fix that so it looks like a question mark. So chat with your neighbor about that. The graph shows what happens if the NaOH is 0.1 molar. We want to know what happens if we were to change it to 0.2 molar. What would happen to that graph? Actually, maybe I should start with this. What volume of 0.1 molar NaOH is required to get to the equivalence point? Tell your partner that. What volume? Oh, 0.1 molar NaOH needed to get to equivalence point. This should be easy. I'm going to start counting by tens. You guys are going to tell me when to stop or if I've gone past. 10, 20, 30, 40, 50. Yeah, we're going to stop because what is the volume needed to get to the equivalence point? We recognize the equivalence point because it is the point where the graph goes vertical, okay? The equivalence point is where the graph goes vertical. Now, what if we changed the molarity of NaOH from 0.1 molar to 0.2 molar? What would happen to the volume needed to get to the equivalence point? Would it be the same volume? I'll give you three choices. Same volume, half the volume, 2 times the volume. You can vote either A, same volume, B, half the volume, C, 2 times the volume, or D, what have we done with our concentration? Going from here to here. We've doubled the concentration. So will we need the same volume?
Probably not.
Probably not. Now the question is, are we going to need more or less? We're going to need less because we've got more moles in the same volume. Does that make sense? So it's going to be half the volume. So it would be 25 milliliters. So we could actually do the calculation. We could say we used 50 milliliters of 0.1 mole per liter NaOH, which is 5 millimoles of NaOH were needed to neutralize the acid. Yes? So if we needed 5 millimoles to neutralize the acid, what volume of our 0.2 molar, I mean, this is sort of complicated. I wouldn't do it this way. I'd just be like, the concentration's twice as much, and so I need half the volume. But if you want to do it like by dimensional analysis, you can say, okay, that gives me 5 divided by 0.2 is, should be 25, right? Milliliters. I think that's overcomplicating things. You can just say 25 milliliters times 0.2 moles per liter will give me 5 millimoles, which is the same as before, which is what we wanted, right? Because that's how much it takes to neutralize it. I think that's an easier way of looking at it. The other way is a little convoluted. And I don't know if this is helpful to you, but what it shows is that it shows that here, at this point right here, this goes down here, all we have is the acid. All we have is H plus and Cl minus. That's it. H plus, Cl minus. Right here, this is halfway to the equivalence point. Do you remember we talked about that, the half equivalence point? You might have missed it. You might have been away for that. So this is the half equivalence point. Half of the acid is gone because we have, and we end up with H2O, an extra H2O. And the Na is floating around because it came with the hydroxide, right? Now, once we have complete neutralization, we will have two H2Os. Dear God. I just want to draw a circle. Why won't not let me draw a circle? Circle. I'll go slowly. There we go. Yay. Okay. So we neutralized one of the hydrogens that we made water. We neutralized a second hydrogen and we made water. And the only things left are Cl minus and Na plus. And do either of those hydrolyze? No. So this is our equivalence point. And then after the equivalence point, we have now added another Na along with its friend OH. So we have excess OH. I don't know if that diagram makes it easier or more difficult. If it helps you, that's great. If it doesn't, then you can just ignore it. Okay? Look, what do we have here? What is in our flask for this curve? Base. Because that's what we're starting with, right? We have excess, base. And what are we adding to it? We are adding acid. So excess base, excess acid, and because it is a strong base with a strong acid, what are our products going to be? A salt plus water, and what kind of a salt are we going to end up with? That's going to be a neutral salt. There will be no hydrolysis because it's exactly the same reaction as the other one. It'll be something like NaCl. So you need to be able to recognize whether you're adding the strong base to the strong acid or whether you're adding the strong acid to the strong base just by the direction the curve goes. Okay? That's one of the things that you need to be able to recognize. Now, ooh, this one is exciting. Now we have a weak acid and we're titrating it with a strong base. So down in our flask, this is now a weak acid. And let's assume it's 0.01 molar, just to make it like the other one. What do you notice about the pH? Is it equal to the constant? Does it give you the same as the concentration of the acid? No, it's a little bit higher because weak acids do not dissociate completely. Okay? Now, there's a couple things that you need to notice here. We have a little hill. Right at the beginning, there's a little hill. So at point number 1, there's been no NaOH added. So the pH is low because it is H3O from the acid, but it's a weak acid. So how much H3O do we get from the dissociation? Here's our weak acid compared with our strong acid. Yeah? This is a lot less. Yeah? Because the dissociation is not complete. That means that your weak acid strong base titration will start at a higher pH. Okay, so if we go back here, it starts at a higher pH than the strong acid. And we get the little hill. So right off the bat, if you are asked, is this particular curve a strong acid? Is it the titration of a strong acid or a weak acid? You can look and you can say, oh, little hill. That is a weak acid. You can say, oh, if it's 0.1 molar, or sorry, 0.01 molar, my pH would be 2 if it were a strong acid. It's not pH 2, therefore it must be a weak acid. It is higher. We're going to leave it there for today because we are completely out of time. And you guys are going to do the buffer questions today on pages 85, 86, 87. Let's just do 85, 86, 87. You can leave 88 for another day, okay?